Okay, well, thank you very much for inviting me to this workshop. I am not a specialist in general relativity, and in some sense my talk will be more about relative generality, in a sense that I will show how some concepts which were very useful in the study of certain effects motivated by general relativity are applied in a completely different setting. And in fact, the progress in those subjects was one of the reasons that we could do something in dynamical systems. But just as a little motivation, without too many explanations, is to say something in connection to general relativity. This is a schematic picture of the classical dynamics for a Kerr de Sitter black hole. Actually, strictly speaking, this is from the hyperbolically asymptotic spaces. This is stolen from a paper by Dyatlov and Dyatlov, but I just want to indicate some main features here. The features here are that one has something called radial sources and sinks. These are this L plus and L minus, which sit at the infinity in the cotangent bundle, and those correspond, and you know more about this than I do, to redshift trajectories. The trapped set, namely the set of trajectories at some given energy, which does not leave a complex set, is a photon sphere, at least in the case of Schwarzschild black holes. To get, for instance, to define, for instance, quasi-normal modes, obtain some Fredholm property, one uses complex absorption beyond event horizons. So this, roughly speaking, are the event horizons, and you put some complex absorbers beyond the event horizons to obtain Fredholm properties. So that's basically all I want to say. This is a point of view developed by Vasy, and his talk and Dyatlov's talk will provide more information. On the other hand, in the case of Anosov flows, this is a picture of the compactified cotangent bundle, if you like a fiber of the cotangent bundle, and you have dynamics. When the dynamics, the feature of the dynamics is that one has stable and unstable sets. So this is the unstable one, and this is the stable one, and those, and you have the different properties of the flow. You also have a trapped set, namely the set of trajectories, which now this is a cotangent bundle, so this is the flow. I will explain more. This is the flow of the Anosov flow lifted to the cotangent bundle. There is a trapped set, namely trajectories which do not escape infinity, just like the photon sphere. And this photon sphere has the same type of dynamical structure. It's actually more complicated than the photon sphere because there is less regularity, but it still has the feature of being a normally hyperbolic trap set, which is something I will explain. Again, to obtain various Fredholm properties, one does use complex absorption, and that one does instead of past the event horizon near the fiber infinity. So somehow the point of view, I mean, this has long tradition, but the point of view of Faure Sjöstrand was to look at the problem of Anosov flows as a scattering problem. Scattering problem in the sense that what you think of infinity or the black hole boundary is the infinity in the psi variables, because this is on a compact set. So this is a very general introduction. I will define now everything, and in fact start in a very basic way. So what this talk is about, since this is something that probably is very far from the topics of this conference, is about continuous dynamical systems. And a continuous dynamical system, well, that is a family of diffeomorphisms generated by some smooth vector field over some manifold, okay? And my vector fields I will consider are non-degenerate, namely they never vanish. So well, a set of flows, so this is a little technical, but this will be flows that will appear later, are contact flows. Contact flows are a generalization of Hamiltonian flows. All the dynamical flows appearing in, that I know of, appearing in general relativity are Anosov flows. Not Anosov flows, far from it, are contact flows. So think about it simply as if it was a Hamiltonian flow restricted to an energy surface. That is an example. An abstract definition is that this flow is really defined by one form satisfying a non-degeneracy condition. And this flow is in the kernel of the differential of this one form, and it's dual, if you like, to this one form. So this is a contact, an example of, definition of a contact flow. So here's an example. Actually, I was looking just to prepare numerics for the talk, just to do something. I was looking for the simplest possible flow exhibiting chaotic behavior. So the famous one is the Lorentz attractor. But Lorentz attractor is very, I mean, you must have all heard about the Lorentz attractor because that's part of popular culture. But this is an example. This is a simpler chaotic system, partially chaotic system, Nose-Hoover oscillator, which is an example of a contact flow on R3. This is the vector field, and this is the contact form, okay, in 3 dimensions. So now, you know, in a system like this, what you have, as in typical system that's easy to write down, you always have some parts of the system which are quasi-periodic and which are chaotic. So the way to see the difference is that you can take the plane x3 equals to 0 and look at trajectories which hit that plane and plot that. So each color here corresponds to just one trajectory hitting this plane repeatedly many times. And you have places of complete integrability, namely the red zone here, and there's a little bit of it here, which correspond to quasi-periodic trajectories sitting on some invariant tori. And you also have chaotic trajectories. Those red points here, blue points here, are just iterates for for much longer times of this one trajectory, okay? So it has both behaviors. But unfortunately, it's very hard, even though in practice most systems are mixed. In practice, it is very hard to study mixed systems, and mathematicians either study completely integrable systems or purely chaotic systems. So my talk will be about purely chaotic systems. So an idealized model for a purely chaotic system is an Anosov flow on a compact manifold. So Anosov flow on a compact manifold is a flow, phi of t, which has the property that at any point of my manifold, the tangent space decomposes into 3 directions, or three subspaces, which are invariant under the flow, and which have properties that along the unstable direction, you have contraction, you have expansion, or if you like, contraction for negative times, and in the stable direction, you have contraction for positive times. So to present it visually, if I'm in 3 dimensions, and then in my space is 3-dimensional, in that case, I have the neutral direction of the flow, so this would be the neutral direction, yes. And then I have, say, unstable direction. Unstable direction means that if I move in negative times, I contract. And then I have stable direction, so this means if I move in the positive direction, I contract. And this is what Anosov flows are. It is easy to write down. It's hard to prove that a given flow is Anosov. And the main feature, and this is why, so this is a theory now, the main feature of these things that are structurally stable. A small perturbation will keep this property, though you may lose regularity. And one of the main features here is that the dependence on this x is very irregular, you know, in general. Excuse me. So an example of an Anosov flow is a compact Riemannian manifold with negative curvature. So in that case, I have a manifold, oops, sorry, this should be M, not X. You know, this is like in MATLAB, you can of course have X is equal to S star of X, the factorial of, well, maybe you don't know MATLAB. So in any case, this would make sense in MATLAB, but not in mathematics. So this is M here. It's the directions of unit length. And then the flow is just the geodesic flow, which preserves the cos-sphere bundle, and that is generated by the Hamilton vector field of the metric restricted to the cos-sphere bundle. It is a contact flow because you have a contact form, which is just the first fundamental form restricted to cos-sphere bundle. So now, the Pollicott-Ruelle resonances, which for those who have sort of ever seen this, are the dynamical analog of quasi-normal modes for black holes, are defined or concerned correlations of the flow. So what is a correlation? To study, this is the definition. correlation means that I take two functions, which are, say, smooth, though could be less regular. My flow has some invariant measure, and what you do, you integrate the pullback of f by the flow, or I take here negative time flow, and integrate against g. This correlates the flow. If you like, this is evolution of some observable, and this is your testing function. And, you know, in all experiments, all you measure are correlations, because you have something evolving, and then you test it somewhere. So correlations are a natural object to study, going back to, I don't know, Gibbs 150 years ago. Now, a power spectrum, in sort of physical vocabulary, is just a Fourier transform of correlations, and it makes sense for imaginary part, for imaginary part of lambda sufficiently large, because you always, I mean, this will always make sense. But it turns out that this actually continues meromorphically to the complex plane under some reasonable assumptions. And this pose of that guy are the Ruelle, Pollicott-Ruelle resonances. So here is kind of a fanciful rendition of that. When you take a Fourier transform of something like this, it typically looks like that. So if you go to any lab, we were in a lab in Nice just a few days ago, and there, you know, on the screen, you see such pictures. Huh? This is now frequency picture, and the point is the sort of anthropomorphic interpretation of this picture is that you would like to associate to this continuous object some discrete object, because we always want to feel that there is like a, you know, an individual attached to a phenomenon. But that really is a figment of our imagination in a way, because it's a continuation, meromorphic continuation. But these are nice things to study. So, you know, you have things which are closer to the real axis. They have sharper peaks because imaginary part is smaller. And then when they are further, you have some less pronounced features of your power spectrum. Now, mathematically, as I said, these things have been studied by Ruelle and Pollicott originally, then by many other authors. But in the last decade, there has been significant progress on understanding of these Ruelle-Pollicott resonances, more in the style of how we study resonances in, say, general relativity or scattering theory, namely, or number theory, where there are, say, zeros of L functions, namely as eigenvalues of some non-self-adjoint operators. And the non-self-adjoint operator is the generator of the flow. Well, I divide it by I to make it self-adjoint. So you may say I said something completely stupid now, because I say I take V. Suppose I have a measure which is invariant. If I take the generator of the flow, then 1 over IV is a self-adjoint operator, formally self-adjoint operator with respect to this measure. But the main point here is that you change spaces on which this operator acts. This operator has a spectrum which is just the whole real line as a spectrum on L2 with respect to this invariant measure. But if you change your spaces, you introduce something called anisotropic Sobolev spaces, what you get is a Fredholm property, provided that the imaginary part of lambda is sufficiently, is bounded from below by minus s, where s is the index here. And these spaces are closely related to Sobolev spaces. They are contained in some rough spaces and contain nice spaces. But of course, there's a subtle definition depending on the properties of the flow. So, but the point I want to make is that this operator now becomes Fredholm, and studying these things rather than go through correlations, which would be very hard, is done by studying spectral properties of this operator on funny spaces. Okay? Okay, so I now want to show you a real-life example. So, of course, there's no real-life example from general relativity, since despite an awful amount of time and treasure spent on it, there is no direct observation of gravitational waves, and consequently you cannot take correlations and take a power spectrum and see anything. But, you know, the untold amount of money was spent on this, both in the US and in this country, or well, in Europe. So here is an example from climate models, which is a recent paper. These are actually very serious people, though, yes, no, I know, but I checked, you know. But whether the work is serious, I mean, that's maybe open to some debate. But what they look at is some climate model, very complicated. These are actually, you know, real PDEs. You know, you study PDEs, you apply sort of finite dimensional chaotic dynamical system theory to much more complicated objects. You know, you do your stuff. And what they were interested in was a parameter dependence. Delta is some parameter in the climate model on the distribution of Pollicott-Ruelle resonances. And this is now lambda, which is here measured in cycles per year. And you see the peaks, just like in my previous picture. And you see that, of course, you could see that, and I'll come back to this, imaginary and real parts depend in a very rough way on this parameter delta, because, you know, you can sort of see that the peaks have different widths and so on. So that is reflected by some rough dependence on this Ruelle-Pollicott resonances. Okay, so one way, so here is a kind of an easy way to define Ruelle-Pollicott resonances. And this was a question that Liverani asked us, namely whether one can define Ruelle-Pollicott resonance. Pollicott, I guess this is France. One really says Ruelle resonances in France. So Ruelle resonances using the following theorem that we proved with Dyatlov, which is this, namely, you take your vector field, you make it self-adjoint, just because we just used to scattering theory pictures, so we prefer self-adjoint operators. And what you do, you add to this a dissipative term, namely the I times epsilon Laplacian. Now this operator, we are on a compact manifold in this talk. So we are on a compact manifold. So this operator here now is perfectly Fredholm. You know, it's an elliptic operator when epsilon is non-zero. So this elliptic operator has discrete spectrum. And the point is that uniformly on compact sets, so namely for lambda j's in a fixed compact set, lambda j epsilon converge to lambda j as epsilon goes to 0. So this is kind of an easy definition. So at least according to Liverani, who asked this question, this was previously known only for discrete systems, namely for iterations of a map, in which case what one does is for correlations we're pulling back by the flow. Here you pull back by your application, by your function, and then you smooth it out at every step by some smoothing operator. And what was proved by this author, by Liverani and his collaborators, following some very general results with Keller, is that in this case you have this type of behavior. Okay. And you know what sorry, so here are some comments. So as I remind you, I consider very simple thing. I just take 1 over I vector field and I add to it I times Laplacian. I know you can say too many i's because, but you see, this is self-adjoint. This is now anti-self-adjoint. And people who, you know, I will explain that this was the point of view of Faure Sjöstrand, is that one should think about it as a scattering problem. And in scattering theory, our principal operator, namely this operator here, should be self-adjoint. So this is our excuse for these i's, okay? Now, the dependence on the spectral projections on epsilon is smooth, but it is not analytic. So it's smooth up to 0, but it's not analytic. Because you see, if I switch epsilon, sign of epsilon, this operator is still perfectly Fredholm, but the limit is very different. The limit is, in fact, complex conjugate of lambda j's. So the dependence is not analytic. The stochastic interpretation is the following. First, for instance, let's now suppose V is equal to 0. Then the standard interpretation of the heat flow is by considering Brownian motion. And then the heat evolution is given just by expected value of f evaluated at the Brownian motion point. So here, instead of Brownian motion, one considers the Langevin equation, namely one takes the vector field and adds to it a little Brownian motion. And this is, so what it means is that, and this is somehow, you know, philosophically important, because this means that these resonances are defined as limits of something where you have some sort of noise added to your system. If this wasn't true, then the whole thing would be just a figment of mathematicians' imagination. I mean, it probably still is, but you know, we can now claim. Well, those are these climatologists, you know. Now, what is really strange, and I must say this is a little embarrassing, I never thought about this, but while preparing this talk, I realized actually the same definition applies to in all other settings. Namely, if you take a scattering resonances, you take, say, potential on the line, you add to it, now you see no I here because this is a self-adjoint operator. Now I take out some operator which will become elliptic near infinity in each sense. Same thing is true. It's a little tricky to test it numerically, but I ran it on comparing to the code by David Bindel against a simple potential. It's not so bad, you know. It works. There's some subtleties in implementing this. So I was at first a little surprised, but I asked Sjöstrand, and he thought, well, it seems clear. We still have to prove this, but I have no doubt it works. But I'm surprised a little bit because I've been in this business for 25 years, and I have never thought of this. And I don't know. Maybe it's well known, but I don't know. Sjöstrand also didn't know any reference for that. It's not probably as useful numerically as I at first thought, but it's nevertheless a kind of easy to present definition because everybody knows if I take this operator, it has discrete spectrum, it limits R resonances. And of course, this also works for quasi-normal modes for black holes. However, you have to in advance know by some other method that those quasi-normal modes are well defined, and only in the region in which they are well defined you will have in compact sets convergence. So just to show, and this was my motivation for looking at the simple thing, was I wanted to run a comparison of a chaotic trajectory and a trajectory which is stochastically perturbed. So here is an example. So of course, you add some Brownian motion, not so small a perturbation, and you see that, of course, it does not follow the chaotic trajectory, but somehow it has similar features as the chaotic trajectory. And the same thing is true for smaller epsilon. And you could study decay of you could explain correlations. You could explain correlations for so if I wanted to look at correlations of now this modified stochastic flow, that's very easy because the eigenvalues of this operator P epsilon are going down a lot into the complex because I have I epsilon Laplacian. So this means in any strip, the number is finite. So I could easily expand my correlation in terms of those guys. And of course, this means that one can use those things to approximate correlations. Though of course, it's a smooth expansion, but for large times you will start having corrections depending on epsilon. So I recall the theorem. So it's not a difficult theorem. So you add this Laplacian, and then uniformly on compact sets you have this approximation. So this is a fanciful rendition. This is actually unlike the other figures. This is just an illustration obtained using a random number generator with some features that you see the circles are fanciful representative of stochastic approximation. They will actually lie below a parabola at large values. These ones are fanciful rendition of Ruelle Pollicott resonances. And approximation is excuse me, uniform and compact sets. Now I have another line here, because if I want to, and this is important, if I want to have a behavior, a gap in the spectrums, and then consequently know that I can write down my correlations using these guys in some useful way, it's important to have a gap so that I know there are only finitely many of these guys in that gap. But before going, I'll say something more about this, but before going there, let me just give some general comments about the proof. So the proof uses the microlocal approach that I already mentioned of Faure Sjöstrand, and it uses the radial point propagation of singularities estimates due to Melrose. Those estimates were proved to explain in some general, to explain the general framework for scattering on asymptotic Euclidean spaces. And Vasy used them exactly to give a microlocal description of the redshift effect and applied it to meromorphic, among other things, to meromorphic continuation and definition of quasi-normal modes for Kerr de Sitter black holes. But actually, I should mention this, that we actually, as I mentioned in the abstract, we use these ideas to give a simple microlocal proof of a conjecture of Smale. So here is this conjecture of Smale. That conjecture was proved just a few months. We actually didn't know about this by Giulietti Liverani and Pollicott, since we're not specialists. We were just interested in something else. And the conjecture of Smale, actually it wasn't exactly stated like that by Smale, but said the following thing. You define something called the Ruelle zeta function. The Ruelle zeta function is a product over of a primitive geodesic, so primitive primitive orbit of the flow. If you have a flow where you have a trajectory, of course this trajectory can go around many times. It's no longer primitive, but if it goes around once, that's the primitive geodesic. You don't count the ones which go around more, and you take a product over those guys. This converges for large values of imaginary part of lambda, and the point is, the conjecture was, that it continues meromorphically to all of the complex plane. So the idea, and the reason for investigating those things has a long history that I will not recall here, is that this is the analog, if you like, of the Riemann zeta function, in which the primes are replaced by the exponentials of the length of orbit, primitive closed orbits. And one of the motivations of Ruelle and dynamical system specialists was to prove prime geodesic theorem, namely laws for counting the number of geodesics, length of geodesics, which were of course modeled on the proof of the prime number theorem using meromorphic properties of the zeta function. So there are many earlier works on this, and these are just some of them, on various aspects of that. And I will mention what is the sort of the point of the proof of this result. Okay, so I return back to my picture, and I have a few more comments to make. So the first comment is, which I already made, is that the spectrum of the operator P epsilon lies below a curve like that. That's pretty obvious. I have an operator which is a vector field plus I Laplacian, well, Cepheid-joint vector field plus I Laplacian. And so of course eventually Laplacian dominates. So imaginary part has to be very negative like that. So in particular, only finitely many eigenvalues for P epsilon in a strip. The approximation is only uniform in compact sets. I said this, but in fact it has to be like that because there's a recent, well, he's writing it now, a student in Berkeley, result which says that in a sufficiently wide strip, there are always infinitely many Pollicott-Ruelle resonances for any Anosov flow. And, well, the last question here is for what systems do we have a gap? For what systems do we have a gap, namely a situation in which there are only finitely many resonances in a strip? Okay, so real-life investigation of the gap. We go back to the climatologists. And here is a picture. I'm not going to explain it. For this model, they use actually a discrete model. They start with a continuous one, but then for numerical reasons, they do a discrete one. So if you like this disk here, to obtain the Ruelle resonances that I had before, you should take a log of this value. So for instance, log of 1 is 0. That corresponds to the resonance at 0. And log of these guys would give you resonances on the line, because log, you know what I mean, log is not a one-valued function. So if you take a log of finitely many points, you will get a whole line of values. So, but it's the same thing. And now they investigate the gap. They are interested in a gap between the circle and the rest. And this is, their model, was some model for El Nino, which was some major event. I remember this from the news, but I forgot exactly what it was. But in any case, it was a big deal. So it's not funny. I think it was a very destructive, climatically, very destructive phenomenon. So what you have is, this is a slow mixing regime. Slow mixing means that the gap is very small. And you see the gap is small. This is this parameter. And in another range of parameters, the gap is large, but the dependence on the gap with respect to this parameter is rough. And there are places where, in fact, you don't have a gap. So this means that there is sort of no decay of correlations. But here is sort of an example of those things calculated for their very complicated model, which is infinite dimensional. But somehow they belief, which must be true, that this infinite dimensional model is dominated by some finite dimensional phenomenon. Because ultimately, we really, can only understand finite dimensional phenomena Okay, so this is from this paper which just appeared in Proceedings of the National Academy of Sciences. Okay, so now I go to more concrete, mathematical concrete things. The mathematical investigation of the gap. So we return to correlations, and the gap, from the point of view of correlations, corresponds to the fact that one has a strip without resonances. So this means if I look in the power spectrum, this means that the power spectrum is the Fourier transform of this guy. It means it does not have any poles in a strip. And then by just deformation of the contour, you could believe that you will pick up only one. There's always a resonance at 0, because you have a vector field, you apply a constant function, you get 0. So in a situation when you have the 0, 1, just like in these pictures here, this is the 0, 1, always there. 0 because 0 is a log of 1. So I have the exponential, so that corresponds to exponential decay of correlations. You decay to the product f and g. If this just goes to this, that is a classical thing called mixing, which again goes back to Gibbs 150 years ago. But here is the exponential decay of correlation. So that has a long tradition of study in constant negative curvature. These are all the Berkeley results of Ratner and Moore. For constant contact Anosov flows, and this is why I introduced contact Anosov flows right in the beginning. This was done, Dolgopiat considered some different setting, but somehow the contact structure as being essential for the gap, I believe, was pointed out by Liverani. You have this exponential decay of correlation. A much finer result was obtained by Tsuji, who obtained, he estimated the size of the gap, the size of the strip in which there are only finitely many Ruelle-Pollicott resonances, and then expanded the correlation. So you see, you have I made a simplifying assumption here that all resonances are semi-simple. And in fact, it's a result of Dyatlov, Faure, and Guillermo that, for instance, in constant negative curvature, all resonances are semi-simple. So here you have a resonance at 0. That corresponds to this being 1, and then Vj and Uj are just the function 1. Okay? And then we have here the decay rate with a gamma naught, which is essentially a form of Lyapunov exponent. It's the best constant for which this is valid for every delta. And these Vj's and Uj's are the solutions of the equation 1 over I, V, applied to, I forgot which one, Uj or Vj, Uj, is equal to lambda Ju, with the condition that the wavefront set is contained in the unstable directions, and the wavefront set of the complex conjugate of Vj is contained in the stable directions. So the next result is, is this gap uniform with respect to epsilon? It's not surprising that it should be, because after all I'm adding damping, but it's not, if you want uniform results, it's not so completely obvious, at least wasn't to us. So here is another result. Now suppose we are on a manifold for which we have a contact Anosov flow, so typically an energy surface for a Hamiltonian flow, and we take this operator P epsilon. Again, we add this diffusive term. And the statement now is that there exist some numbers such that, in fact, outside of some fixed box of this depth in the complex, the resolvent of this operator is polynomially bounded as energy goes to infinity, but of course not on L2, because as epsilon is 0, this is the spectrum is the whole real line. So obviously this cannot be on L2. So what it is bounded on from say high regularity Sobolev space to low regularity Sobolev space. In fact, it's bounded on those anisotropic Sobolev spaces, which have these properties. And this is the same constant as in Tsuji's result. So this means that the result is uniform with respect to this. And in fact, there's a recent paper where there is an analogous result for maps on the torus in the same spirit as in the results of Liverani that I mentioned before. So I would like to indicate a little bit the proof of this result, and the proof also of the first result, and of the proof of the Smale's conjecture. So this is the result one wants to prove. We take this operator with this diffusive term, and we want to show that this is polynomially bounded in lambda for some funny spaces in this strip. So this R simply means that I'm excluding some compact set in which there will be finitely many of these guys, because I already know that on a compact set I have uniform convergence to the actual Pollicott-Ruelle resonances, and those are discrete. So to prove this, we do this, and it's not just a complete, just attachment to one's own method, but I think that sort of reflects the physical structure of the problem. We make a semi-classical rescaling. So this means that we will simply to have dynamics in compact sets as opposed to go to infinity, come back, and so on, because that's how it's done in quantum mechanics. What is we rescale, so rather than consider lambda going to infinity, we will have z, which has the real part fixed away from zero for this problem, because we are interested in things away from zero, and with the imaginary part of z greater than this. This is just the rescaling. So you can see that this region here is just the rescaling of this, and you can do dyadic things, and you get all of this to infinity. And what one wants to prove is that if I multiply this operator by h, which just means this, I take now hv, so this is now a semi-classical first-order operator. This is a semi-classical second-order operator. Of course, I now have to multiply by epsilon over h. And what we want to prove, well, we want to prove that the inverse of this in this set is polynomially bounded in h. It's bounded by h to some negative power. The symbol of this operator, so semi-classical symbol of this operator, is very simple. The operator, this vector field, and this is why I here is important, because then we get a real symbol, but it's just a covector. So now we are in the cotangent bundle of the manifold on which we have a flow. So for instance, it would be the cotangent bundle of the cosphere bundle in the case of negative curvature, manifold of negative curvature. So we have this operator here. This is the real and imaginary part. And what you observe here is the following thing, that if this is zero, if the real part is zero, then psi v of x has to be close to 1. But when psi v of x we are always in dimension bigger than 1. So when psi of v is bigger than 1, or is around 1, that means that psi is bounded away from 0, obviously. And psi is bounded away from 0, this means that this time is elliptic. Yes. So what you have here is, of course, there's a slight, one has to be concerned about this factor here. But it's not unreasonable, and it is in fact true, that if epsilon is bounded away from 0 to the tune of h squared, you actually have a bound of this in a strip. And in fact, you can get any strip here. That's not unreasonable. So what does it mean? Well, that means that if epsilon is of size h squared now, or less than h squared, this is a lower order term in the semi-classical sense. So here is, I repeat the lemma. When epsilon by h squared, we have a nice bond in a strip. So we can assume, as I said, that epsilon is less than some constant times h squared, and then the Laplacian becomes a lower order term. So there's, of course, some issue about it being not a lower term as a differential operator, but if everything goes well, it is sort of a lower order term. And then we can use very general results of with Nordenmacher, which on scattering for normally hyperbolic trapping. And in fact, it was nice that we could just basically use that result as a black box to prove this because of this lemma. But I will explain this. So what is normally hyperbolic trapping, and how does it manifest itself here? So I recall this point of view of thinking about the flow as a scattering problem with infinity corresponding to fiber infinity. So here is a picture. I can think of the flow on the base, on x, is just the exponential of TV. V is the generator of the flow. The pullback by the flow is the Schrödinger operator. Excuse me. The Schrödinger operator, well, where P is H over I, the generator of the flow. And then the Hamilton vector field of this operator is just the symplectic lift of this flow to the cotangent bundle. And then you have dual stable and unstable directions, and this is where the flow really takes place. And in scattering theory, the crucial object in this business is the trapped set. The trapped set is the set of points on the energy surface for which the flow does not go to infinity. In this case, there's no infinity in X. This is a compact manifold. So in fact, this setting is much easier than scattering theory. Because in scattering theory, even though we deal with operators which are elliptic, we still have to always deal with this psi infinity. And it's, it's a nuisance. Here, this nuisance is gone. It's much simpler. For instance, when energy is equal to 0, what is the trapped set? Well, the trapped set in that case is the zero section, namely the vectors psi equals 0. Well, why is that? Because if I'm at the energy 0, that means that psi times v is equal to 0. So this means that psi kills the direction of the flow. So this means psi has to be in the dual space of the stable or unstable directions. But the stable or unstable directions either contract, but then they go to infinity in this direction, or they expand. So this means that when psi v is equal to 0, for time going to infinity, either in positive or negative directions, you will go to infinity. And hence, this is the trapped set are only vectors of psi equals to 0. Now we come to normally hyperbolic trapped sets. And this is related to general relativity because the trapped sets for black holes are normally hyperbolic. And in this case, we now work away from zero energy. Away from zero energy, I look at the slab of trapped sets. I look at a bunch of them at different energies. And it turns out, in the setting of Anosov flows, but this is now a general definition, if you like, that K is a compact, smooth, symplectic manifold. So for instance, for those of you who are, say, familiar with, say, I suppose everybody's familiar with Schwarzschild black holes, in the case of Schwarzschild black holes, this would be the cotangent bundle of the sphere, when I would say take psi in some fixed region, the energies, yes, so which is very nice symplectic manifold. And then the point is that every tangent space at point, so rho, if rho is an element of this K, the tangent space of the cotangent bundle of X decomposes, well, into tangent space of K plus two subspaces where you have expansion and contraction. So this is what normally hyperbolic means. Normally hyperbolic means that you have something which is smooth. The flow here can be complicated and you don't know what it is, but in the transversal directions, it is either expanding or contracting. So, of course, in the case of, say, Kerr de Sitter black holes, these are very nice examples of completely integrable, normally hyperbolic trapped set, because the flow is completely integrable. For instance, in the case of Schwarzschild black holes, it's just the flow on the geodesic flow on the sphere. So, unlike, of course, in that case, in the black hole case, there is an extra feature that I won't talk about. Probably Dyatlov will talk about that. There's something called R-normally hyperbolic. There, the dynamics has additional nice features which make this structure stable under perturbations. Here, it's rather nasty, in a sense that you have rather nasty dependence on rho of this distribution. So here is a fanciful rendition of this. You have your trapped set. This trapped set, of course, is invariant. And then you have trajectories, and then you have, which sort of come close to it, and you have expansion, expansion and contraction in those corresponding directions. So the point, in fact, the results that I mentioned before, in particular the result of Tsuji, exploit the structure, and the result with Nonnenmacher gives a very general argument. So let me say what it was. We considered the case where we had operators of this form, where we added a complex absorbing potential near infinity, And the point is that this complex absorbing potential defines the trapped set, which comes, of course, from the actual flow on this non-compact cotangent bundle, is the same as the trapped set defined using the complex absorbing potential. Namely, the trapped set is equal to the set of trajectories on this energy slab which never enter, which are always contained inside of the zero set, excuse me, of W. So they always live in a place where there's no damping. And there's some, well, this is a fact that we have ellipticity near infinity, and there's a technical assumption that I will mention. And the statement of our result with Nonnenmacher is that if the trapped set is normally hyperbolic, then you have a nice bound on the resolvent in this strip where gamma is the same, though this is, P can be very general. In fact, our motivation was quantum systems, because these normally hyperbolic sets also arise in molecular dynamics. So here is, so then you have the same constant. So here is the statement of this result. Huh? And I won't prove it, but I'll give a proof by picture. The proof is a little technical, but the idea is that you can localize near the trapped set. So trapped set is a symplectic manifold. So by the uncertainty principle, the closest localization to this trapped set is within like h1/2 distance to the set. So what you do is you cut off to h1/2 distance times a large constant to the neighborhood of the trapped set. You apply your propagator, and then you cut it off again to this neighborhood of the trapped set. And then using some microlocal weights in some exotic classes, you handle stuff outside. Now, when you do this nearby, you simply have, well, first of all, in the small neighborhood, the flow, this is where it gets a little difficult. The flow on K can be complicated. In this case, actually, it's simple, but in the general case, it can be complicated. But in the transversal direction, you can linearize it because you work in an h1/2 neighborhood. So you can go well past the uncertainty principle in your quantization in some new Planck constant, which corresponds to your constant, which is the size of the h1/2 neighborhood that you took. And using this contraction expansion, you show some hyperbolic dispersion hyperbolic as in hyperbolic dynamics, not hyperbolic equations, dispersion estimates, which give you this type of gap. Okay, so, and of course, there are other works on normally hyperbolic trapped sets, the work of Gerard and Sjöstrand, the analytic case, and in this is a mathematical paper. Wiggins has a whole book on normally hyperbolic sets with applications to molecular dynamics. As far as I know, the connection to black holes was pointed out first in my paper with Wunsch. Ford Tsuji have many works showing how in the contact, for contact flows, you can get very fine description of scattering, of Ruelle resonances. And Dyatlov has results for black holes with asymptotics plus some results in the setting of anormally hyperbolic trapped sets. So we have now an estimate like this with this W. And if we go back, and the W that I'm going to take is our Laplacian, because epsilon over h now is of size h. So this is a lower order term. So this does not affect my definition of the trapped set, because trapped set is only defined using the principal symbol of this operator. And f is some function which is like t for sufficiently large t, so that this provides ellipticity near infinity. It's just like Laplacian near infinity. So this, if you like, provides damping near infinity. So this operator here is just h times my p epsilon operator minus this damping. This is the operator we want to show that the gap is uniform with respect to epsilon. So consequently, if I just take this result, rewrite it this way, we get this bound. On the other hand, we want to prove damping. Now to obtain estimates which are valid near infinity, we put a damping near the trapped set. And the crucial result is that if I take this h p epsilon and I subtract q, which lives near the trapped set, which is identity near the trapped set, one has a bound, but on those anisotropic Sobolev spaces, because now we have to deal with infinity. And for epsilon equals to 0, that was the crucial component of this microlocal proof of Smale's conjecture, because all you have to do to prove it, I can't do this now, but all you have to do to prove is to estimate the wavefront set of this semi-classical wavefront set of this operator for epsilon equals to 0. And modulo background material, it is a very simple argument. So here, this HS spaces are this version. Is another, yet we use a slightly different version. It's very close to the one of Faure Sjöstrand, but it's a little simpler. But it follows the same tradition. So proof by picture, I can't really give a proof, but let me give a proof by picture of this estimate. Now, you have this is the compactified cotangent bundle. So this circle here is infinity in psi, okay? Now the flow goes from the stable set to the unstable set. K corresponds to projection to infinity. This is the stable set, this is the unstable set, this is the trapped set. This is the trapped set. So now you want to show that this operator is invertible. Well, how do you prove this? Well, you use propagation results by showing that you can approximately solve the equation with some errors which are like h infinity, and eventually if you do it globally, you can invert the operator. Now, the standard propagation estimate is an estimate of Doistemat Hermander, which will tell you that, say, if I'm here, if I want to control this, if I have control over the operator, which I do because I'm inverting the operator, so if I have control of the operator applied to a function, then to obtain estimates on this operator, say on the set A3, I need to know the operator on the set C3, because C3 controls A3 by propagation. And that is the result of Doistemat Hermander. That's the standard, that's light propagation. That's all the simple fact that, you know, it's bright there because the sun shines from over there. So the radial estimates of Melrose say that if you have sufficient a priori regularity, and this is the only feature that I will mention of these anisotropic Sobolev spaces, that they are very regular near these stable directions. And the radial estimate of Melrose says that if you have a priori regularity here, then you only need to know that the solution is controlled purely by the, so U is controlled by PU in A1. And that's your starting point. You don't have to have any other control. And then you move along. Here you put Q, the damping. So this is the only place that could cause you trouble, because this is where you have the trapped set. That's where non-invertibility comes from. But you put a damping there, so here everything is elliptic. You can control here. Then you move in. Then this, Hermander, gives you control here. Then, again, the radial estimate will tell you that you can control what happens in A2 by what happens in C2. But you sort of move along, so you got C2 from those other pieces. And then you have control in A2. So by taking partition of unity, blah, 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 you control U by PU modulo H infinity. And of course, since it's all nice spaces, there's a Fredholm operators, that was the point to start with, you can invert. So we have an estimate with damping near infinity. We have an estimate with damping near the trapped set. So now we want an estimate without this damping and without this damping. So if you like, this is damping here, and we have estimates. And then we have no damping here, but we have damping here, and we have estimates. So for that we use gluing methods. So there are gluing methods based on propagation of singularity, or well, propagation of singularities, or propagation, semi-classical propagation that we did with Burg. And there's a nicer and more general version due to Dachev Vasy. And using these methods, you obtain the bound without these damping terms, which is the result that I mentioned. And to finish, actually, yes, and the version of this estimate too was also crucial for proving this estimate of convergence to lambda j's as we proposed. So let me just say, because really, you know, when you start looking for examples, and you know, you don't need far to look, you look at this room. This room probably has some chaotic trajectory somewhere, but it certainly has plenty of invariant tori. And so it's a mixed system. So can any of this work for mixed systems? And I try, and I talk to, dynamicists, it's just not clear, unfortunately, and there are very few results, and there are only simple models that have been studied. Because what happened, you could, from this sort of microlocal point of view, or PD point of view, you could consider it as a very nasty boundary value problem. Because what happens, let's look again at this Poincaré section. The blue, this is actually not a very, I have a better MATLAB picture. This is the conversion to PDF does some nasty things to this picture in itself. But the blue set is the set, the chaotic C. The vector field, it's an invariant set. So the vector field is tangent to the boundary of that blue set, okay? But that boundary, of course, is very nasty because what it has, it has all tori, on any level, on any scale. And there's no general result, but people believe that, say, you may have decay of correlations, exponential decay of correlation, or even decay of correlation, only under some conditions on this boundary that, namely, you go around those small tori, but maybe if they are somehow small in some sense, dimension-wise, that the decay of Lyapunov exponents, of course, have to be zero as you approach those tori. But suppose the decay of Lyapunov exponents is somehow slower than, the motion around those tori, you may still have decay of correlation. But it seems, I'm sorry to say, it seems like a rather hopeless problem, even numerically, let alone mathematically. But who knows? So I would like to stop here. Thank you.